the D and F block elements. In that D block elements, we call it D block elements as transition elements. General properties of D block elements. Transition metals have incompletely filled d orbitals in their atoms or in one of their common oxidation states. They form colored compounds, show variable oxidation states, usually act as a good catalyst. Most are metals and form complex compounds, and they are exhibit paramagnetism. Means D block elements show variable oxidation state. For example, chromium shows +3 and +6 oxidation state, and manganese show +7 oxidation state and +5, and scandium only show +3 oxidation only, and other all elements except scandium D block element shows variable oxidation states. And stable oxidation state of chromium is +3, and higher oxidation state of first series of transition state is +7 in that manganese. Color of transition metal ion, if Ti +3 means it shows violet color, and the number of unpaired electron is 1, and V +2 means vanadium +2 means it shows violet color, and number of unpaired electrons are 3, and V +3 means it shows green color. Number of V +3 possess green color, and chromium +3 also possess green color. Number of unpaired electrons are 3, and manganese +2 oxidation state shows pink color, and number of unpaired electrons are 5, and Fe +2 also shows green color. Number of unpaired electrons are 4, and Fe +3 possess yellow color. Number of unpaired electron is 5, and copper possess blue color. Number of electrons unpaired electrons is 1. Next one is magnetic properties. Magnetic behavior is due to unpaired electrons. More unpaired electron, greater paramagnetism. If all electrons are paired, if all electrons are paired diamagnetic, magnetic moment mu is equals to under root over n into n plus 2. Sorry, it is full root over n into n plus 2 bm, okay, where n is equals to number of unpaired electrons. In 3D series, ions are generally paramagnetic, and Zn plus 2, cadmium plus 2, Sc plus 3 are diamagnetic. There is no unpaired electron. Means magnetic behavior is due to unpaired electron. Magnetic moment we have to find means we have to use a formula, root over n into n plus 2. There is n is nothing but a number of unpaired electrons. If there is no unpaired electron means there is no magnetic momentum, like that. If unpaired electrons are more, then paramagnetism also more. And 3D series ions are generally paramagnetic, and zinc plus 2 and cadmium plus 2 and Sc plus 3 are diamagnetic. And chromium possess more number of unpaired electron, and molybdenum also possess more number of unpaired electron. Tungsten also possess. So these are possess more magnetic properties, magnetic moment. And Mn plus 5, there is no Mn plus 5 also possess unpaired electrons, like that. And next one is relative stability of oxidation states. Stability of oxidation states depends on electrode potential, ionization enthalpy, and lattice energy. Higher oxidation states are stabilized by high electrode potential, high ionization enthalpy, high lattice energy, and small size of the ions. Common trend in 3D series: Sc is greater than, Ti is greater than, vanadium is greater than, chromium is greater than manganese, and iron is greater than, cobalt is greater than, nickel is greater than, copper is greater than zinc. Means these are in series only. The next one is specific use of some catalyst. If we use Fe iron as a catalyst, it is used in Haber's process, manufacture of ammonia, and V2O5. It is used in contact process to manufacture of H2SO4, and platinum Ostwald process, manufacture of HNO3, and nickel hydrogenation of oils, and FeSO4 or H2O2 Fenton's reagent, oxidation of aldehyde to carboxylic acid, and copper dehydrogenation of alcohols. We have to note important that one is Fe. Fe is used as Haber's process in manufacture of ammonia, V2O5 in manufacture of H2SO4, platinum in Ostwald process, nickel in hydrogenation, copper in dehydrogenation. Okay, next one is atomic radii. In a period, atomic radius decreases from left to right. Mm. As nuclear charge increases, atomic radius will be decreases. As left to right, nuclear charge will be increases, so atomic radius will be decreases. And in a group, atomic radius will be increases from top to bottom. In top to bottom, nuclear charge will be decreases, so atomic radius will be increases. In 3D series, atomic radii of ions decreases with increase in atomic number. And Sc plus 3 is greater than Ka plus 3. These all are in series only. Scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper, zinc. Here we have to note that importance of main important thing is here in this stable oxidations are given, means Sc has stable oxidation state plus 3, titanium also plus 3, like that they are given stable oxidation state. And next one is common oxides of transition elements. TiO, Ti2O3, TiO2. These are basic. How we can identify these are basic or amphoteric or acidic? Means we have to check their oxidation state. For example, oxygen oxidation state is -2. Then titanium oxidation state +2. If oxidation state is less, means these are basic. Like that, Ti2O3 oxidation of oxygen is -2, -2 into 3 -6, -6 by 2 plus -3. In titanium oxidation state is +3. So these are basic in nature. And next one is amphoteric. V2O3 oxygen oxidation state is -2, -2 power 2 into 3 means -6, -6 by 2 means +3. It is also amphoteric, and V2O5 also amphoteric. Like that we have to check their oxidation state. In mm, in Cr2O3, -2 is the oxidation state, and -2 into 3 -6, and -6 by 2 3. These are also amphoteric in nature. And if we consider Mn2O3 also, uh, MnO2 M plus 3 also. Plus 3 means basic. Means manganese highest oxidation state is +7. In that plus 3 is basic only. And VO also basic. V2O3 amphoteric. And MnO2 also amphoteric. MnO3 is acidic. Mn2O7 also acidic. If in manganese +6 and +7 came oxidation state, means we have to consider that one as acidic. If in between, and Fe2O3 also basic, like that. And NiO also basic, Cu2O also basic, and CaO also, Ca2O3 also basic. Next one is catalytic behavior. MnO2 is used as a catalyst in decomposition of KClO3 to oxygen O2. Means MnO2 is used as a catalyst in decomposition of KClO3 to O2. And FeCl3 is used in the manufacture of I2. And V2O5 is used in the contact process. We have already seen. Nickel also used for hydrogenation. Platinum used for Ostwald process for HNO3. And next one is standard oxidation potential and reducing properties. Easy to get higher oxidation states, strong reducing agents. More negative A naught, stronger reducing agent. In 3D series, reducing power increases from scandium to titanium and then decreases towards copper. For example, the titanium plus 3 stronger reducing agent than Fe plus 2. Means we more negative E naught means it is stronger reducing agent. And next one is atomic and ionic radii. In a group, atomic radius decreases from left to right. We have also seen this one. And important points means transition element form complex compounds due to vacant d orbital. They show very high enthalpy of atomization and boiling points. Most of are hard and have high density and good conductor. They form interstitial compounds and show variable coordination number. And next one is magnetic property. When a substance is placed in a magnetic field of strength and the intensity of magnetic field in the substance may be greater than 1 or less than it. If the field is substance is greater than h, it is paramagnetic. Means in the field the substance is greater than hydrogen, it is paramagnetic. Less than hydrogen, it is diamagnetic. Paramagnetic substance allows the magnetic lines of force to pass through them rather than vacuum and show increase in weight. Diamagnetic substance attracts a line of force and is free to move from stronger to weaker part of field. Paramagnetic substance is weakly attracted in magnetic field, diamagnetic is weakly repelled. Paramagnetic is arises due to unpaired electron spin. And the paramagnetic behavior is possible due to presence of one or more single field atomic orbitals, whereas diamagnetic behavior is due to the presence of paired electrons. Diamagnetic material tend to repel line of force and align themselves perpendicular to the magnetic field. And thus paramagnetic substance attracts line of force. Paramagnetic arises as a result of unpaired electron spin in the atom. Diamagnetic substance is one which is repelled by magnetic field. These all are magnetic properties. And next one is alloy formation. Alloy is the solid solution obtained by repelling one metal by another metal in lattice. Formation of alloys in a transition metal is possible due to their small and nearly same atomic size. The transition metals are miscible with one another in molten state which on cooling from alloy. To form alloy, the metals should have atomic radius within the limit of about 15% of each other. Alloys are easily formed between transition metals due to their atomic radii. Transition metals form alloy with non-transition metals like brass, copper and zinc, bronze, copper and mm, are possible. Means transition metals Fe form alloys with chromium, vanadium, molybdenum, tungsten and manganese. To form the alloys, the metal should have atomic radius with a limit of about 15% of each other. Okay. The transition metals are miscible with one another in molten state, which on cooling form alloy. And next one is formation of interstitial compounds. Crystal lattice of transition metals have interstitial spaces. The interstitial spaces in these metals lattice are occupied by small atoms of transition metals such as hydrogen, boron, carbon, nitrogen, etc., and form interstitial compounds. They do not follow definite composition and neither typical ionic nor covalent character, hence are non-stoichiometric in nature. Example TiC, TiH2, Mn4H, Fe3H, VH and They have identical chemical properties of interstitial compounds with their parent metals. These are hard, lustrous, and have electrical and thermal conductivity. These are hard, lustrous, and have electrical and thermal conductivity. Their melting point are higher than parent metal because the metal non-metal bond are stronger than metal-metal bond. They are lighter than pure metal. Hybrids of these elements are used as reducing agent. Metallic carbates are chemically inert and very hard as diamond. Steel and cast iron are interstitial compound of Fe and carbon which are harder than iron and have very hard bridges like diamond. We have to note this important means steel and cast iron are interstitial compounds of iron and copper which are harder than iron and have very hard bridges like diamond, not like diamond, bridges like diamond. Okay. And metallic carbides, it is metallic carbides or metallic borides are chemically inert in and very hard as diamond. Metallic borides or carbides are very hard as diamond. Steel and cast iron are the interstitial compounds of iron and copper, which is harder than iron and have very hard bridges like diamond. And interstitial compounds have high melting point. They are lustrous and electrical and thermal conductivity. And metal non-metal bond is very stronger than metal-metal bond. And the small places occupied by non-metals like hydrogen, boron, carbon, and nitrogen. And next one is transition elements have incomplete field with like d orbitals. We know that they form colored compounds and show variable oxidation state. Paramagnetism behavior due to unpaired electron, diamagnetic behavior due to paired electron, transition metal form complex compound due to vacant d orbitals. They form interstitial compounds with hydrogen, boron, and carbon, nitrogen. Potassium dichromate K2Cr2O7 and potassium permanganate KMnO4. In that potassium dichromate, it is orange colored crystalline compound, act as a strong oxidizing agent. Chromium in K2Cr2O7 is in +6 oxidation state. Preparation means from sodium chromate or potassium chromate. Conversion to dichromate by acidification. It is in yellow color and after acidification it becomes orange color potassium dichromate. And structure. Two tetrahedral and sharing one oxygen atom. Chromium has bond angle 126 degree. Color orange red color. Oxidation strength is strong in acidic medium. And reactions in acidic mediums with I minus. K2Cr2O7 when treated with the I minus, it convert I minus into I2. Means it is a best good oxidizing agent. It I minus to I2, it is involving in oxidation. And reaction with Fe plus 2. It convert Fe plus 2 to Fe plus 3. And SO2. SO2 to SO4 minus 2. Means in reaction with K2Cr2O7 with I minus, it convert I minus to I2. With Fe plus 2 means it convert Fe plus 2 to Fe plus 3. With SO2 means it convert SO2 to SO4 minus 2. Okay. And sp3 hybridized carbon and bond angle is 126 degree and tetrahedral molecular shape. Next one is properties. Deep orange red crystalline solid. It is soluble in water and it is strong oxidizing agent. Stable in dry state. Decomposes on strong heating to chromic oxide. Next one, it uses as a strong oxidizing agent. In volumetric analysis, Morse salt iodine determination. In tanning of leather, In manufacture of chromium compounds, dyes, inks, in chemical tests to detect certain ions. And next one is potassium permanganate. It is purple crystalline compound, powerful oxidizing agent in neutral and acidic medium and basic medium also. Potassium permanganate KMnO4. It is purple crystalline compound, powerful oxidizing agent in neutral, acidic medium and basic medium. Mn in KMnO4 is +7 oxidation state. And preparation. By fusing of MnO2 with KOH and oxidizing with KNO3 or KClO3. When MnO2 is treated with KOH, it gives potassium manganate. It treated with chlorine or oxygen, it gives potassium permanganate. Its properties are dark purple crystals, soluble in water, strong oxidizing agent, on heating decomposes to MnO2, oxygen and potassium manganate. And reactions. Reaction in acidic medium. KMnO4 plus H2SO4, it gives K2SO4, MnSO4, 3H2. In neutral medium, it convert MnO4 minus to MnO2. In alkaline medium, it convert MnO4 minus to MnO2 like the A in that I minus to IO3 minus in alkaline medium. And action with H2. And oxidizing property. In neutral medium, MnO4 plus H2O gives 2 KOH plus 2 MnO2, 3 oxygen. In neutral medium, MnO4 minus converts to MnO2. In alkaline medium, KMnO4 convert into MnO4 minus 2. In acidic medium, KMnO4 convert into Mn plus 2. And uses. In volumetric analysis, self-indicator. In medicine as antiseptic, weak solution. In organic chemistry for oxidation reactions. For purification of water. In qualitative analysis. Next one is lanthanoid series. 4F series. Lanthanoid series. The group of 14 elements from cerium Z is equals to 58. Atomic number is equals to 58 to lutetium. Atomic number is equals to 71. In which last, that is the differentiating electron, is entering in penultimate, anti-penultimate or pre-penultimate 4F orbital, all called as lanthanoids or lanthanoids or 4F series. These elements are nominated as lanthanoids from the element lanthanum, which is a prototype of lanthanoid. Their N-2, that is 4F, and N-1D, that is 5D subshells are incompletely filled. Their N-2 means F, that is 4F, and N-1D, that is 5D subshells are incompletely filled with electron. And general valence shell electronic configuration of lanthanoids is 4F 1 to 14, 5D 0 to 1, and 6S2. As they contain 6 main shells, they are placed in 6th period and group 3 of the periodic table. Actual position of these elements is in 6th period between lanthanum to hafnium, but only for convenience they are placed at the bottom of the periodic table. Means atomic number 57 to 72. And position of lanthanoids in periodic table is confirmed on the basis of the following factors. All these elements have the same number of electrons in valence shell, that is 1 in 5D and 2 in 6S. They have common valency, that is 3. All these elements, that is from cerium to lutetium, have identical physical and chemical properties. In these elements, electrons are progressively filled in 4F orbital and are called as 4F series. Electronic configuration of lanthanoids. Lanthanum, symbol La, atomic number 57, and general electronic configuration is 4f0, 5d1, 6s2. And lanthanum next: cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thalmium, ytterbium, lutetium. And electronic configuration: atomic number barium is 56, in which 6s is completely filled, uh, and from lanthanum and onwards filling of 4d orbital starts. In this electronic configuration, we can observe that in lanthanum, gadolinium, ytterbium, lutetium, uh, there are each 5d orbital has one electrons. Means remaining all are has uh, remaining means they are stable. Gadolinium possesses 4f7 electronic configuration, which is half filled and which is more stable, and ytterbium also possesses 4f14, which is stable, which is more stable. And in this, europium possesses more large size than other elements. And lanthanum possesses plus 3 oxidation state. Actually, common oxidation state of lanthanum is plus 3, and cerium possesses plus 4, praseodymium possesses plus 4, neodymium possesses uh, neodymium possesses plus 2, plus 3, plus 4, and promethium possesses plus 3, samarium possesses plus 2, plus 3, europium possesses plus 2, plus 3, and terbium dysprosium possess plus 4, plus 4, and plus 3, plus 3, and the thalmium and ytterbium possess plus 2, plus 2 oxidation state. Lanthanum show only plus 3 most stable oxidation state by losing of 2 electrons from 6s and 1 from 5d orbital, and gadolinium form only plus 3 more stable oxidation state due to half filled stable of subshell, and lutetium also possesses plus 3 oxidation state due to extra stability of completely filled. Cerium, terbium attain 4f naught and 4f7 electronic configuration by losing 4 electrons from cerium and terbium, having extra stability to empty half filled electronic configuration. Europium and ytterbium possess F7 and F14 are stable respectively due to extra stability of half-filled and completely filled 4F subshells. And uh, samarium and thalmium possess plus 2, and samarium, europium, ytterbium behave as a reducing agent. Ions like CF4, Tb plus 4 act as a good oxidizing agent. Means plus 2 oxidation state is that they act as a reducing agent, plus 4 is there means these are act as an oxidizing agent. And lanthanum show in addition to plus 3 they may show plus 2 and plus 4, and lanthanum show plus 3 common oxidation state by losing 2 electrons from 6s and 1 electron from 5d or 4f. Total numerical charge assigned on the atom of an element in molecule is called oxidation state. Actinoids, the elements in which last, that is differentiating element, is entering in perpendicular shell 5f subshell are called as actinoids. The group of 14 elements from atomic number 103, in which last electrons entering in 5f subshell are called as actinoids. They are called as actinoids because their properties are similar to the actinium, which is a prototype in the series. These elements constitute second transition series. They have identical electronic configuration in valence and penultimate shell. Only thorium and uranium are naturally occurring, whereas remaining are prepared in laboratory. The elements having atomic number higher than 92 and which are synthetically prepared in laboratory by nuclear reactions called transuranic elements. And elements of actinoids are actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. And these are also show along with plus 3 oxidation states variable oxidation state, that is thorium shows plus 3 and 4, protactinium shows 3 4 5, uranium shows 3 4 5 6, neptunium shows 3 4 5 6 7, plutonium shows 3 4 5 6 7, and americium shows 2 3 4 5 6, like that. Along with plus 3, these are process plus 2 plus 4 plus 5 plus 6 plus 7 also. That is the atomic number increases, stability of plus 3 oxidation state also increases. Actinium and thorium shows plus 2 oxidation state. The elements from thorium plus 4 oxidation state, thorium to berkelium. The elements from thorium to americium show plus 5. The elements from uranium to americium shows plus 6, and neptunium to plutonium shows plus 7. The large number of oxidation states are possible in lanthanides due to very small difference in energies. And next one is difference between lanthanides and actinoids. Last electron enter into 4f subshell in lanthanides. They are placed in 6th period. 14 elements mostly show plus 3 oxidation state. Along with them, these are show plus 2 and plus 4 also. Next one is actinoids. Last electron enters in 5f subshell. They are placed in 7th period. 14 elements show variable oxidation states. General electronic configuration of actinoids: vanadium 5Fn and 5Fn 6002 and 7s2. Means 5F1 to 14, 60021 7s2.